So today we'll do something that's slightly different from what we do usually, because I spend a lot of time doing calculations on the blackboard. But I think once in a while it's nice to, show some pictures and some tables and the kind of stuff that is not so easy, to draw on the blackboard. So I'm going to do that occasionally as we progress to this class. Every 3 or 4 lectures, I'm going to have something that is, kind of a PowerPoint thing when I can show some interesting things and facts that kind of complement what we did in the lecture. So because I don't do it every lecture, now in this particular case, I'm going to go back just a little bit at the beginning to special relativity to discuss some things that, in fact, some of you might already be familiar with. And first let me bring up, of course, the picture of the guy that was very influential in developing the early aspects of Einstein's theory, which was Lorentz. Is shown a picture here, the two of them together. And now, one of the very first experiments that was of some relevance to special relativity was the Michelson-Morley experiment. I remember the Michelson-Morley experiment was based on some sort of Fabry-Perot interferometer, where these people tried to detect whether there was a motion with respect to the ether, right? And so they followed the motion of the interferometer over the seasons and over the days and so forth to detect whether there was any sort of residual movement with respect to this ether. And of course, they found a zero effect. So the ether did not seem to exist. And now, Hartel's book, which is fairly recent, has some nice discussion of various follow-ups on these original experiments. And so while the Michelson-Morley experiment was conducted more than 100 years ago, more recent versions, like this one done in 1978, was able actually to establish a bound on the motion with respect to the ether, which is much more stringent than the original experiment. So this is one of those experiments that are trying to test special relativity. We're going to talk more about experiments that actually do tests of general relativity as well. But already in this case, one has been able to progress significantly. And so one of the things that one would be interested in at the level of special relativity is to what extent does special relativity hold? To what extent it is true that you have this local Lorentz invariance, right? And so we have the original Michelson-Morley experiment up here, where you introduce a parameter. I'm not going to go into a lot of details on what exactly these different experiments are doing, but you can see that over the years, one has been able to go down from something that is over the 10 to the minus 6 to something that is more like 10 to the minus 16, 10 to the minus 22 in testing, whether Lorentz invariance actually is true or not, right? And now, besides these tests, of course, there are applications of special relativity that we do, as physicists at least, we do in everyday life. And one of them, again, you might be familiar with this, but is the fact that muons can be used as relativistic clocks. Right now, we have very large amounts of muons that are produced in the upper atmosphere, because what we have is usually a high-energy cosmic ray that hits an upper layer of the atmosphere, proton. Proton ends up hitting some sort of nucleus, usually it's nitrogen or oxygen, and it creates a cascade of particles. Many of them, because it's a strong interaction process, many of them are pions. The pions decay rather rapidly and generate showers of muons. And those muons actually are fairly long-lived. And so the muons that are created in the upper layer of the atmosphere go down and reach the surface of the Earth quite easily. And they are a test of time dilation invariance, because there is a natural clock that is associated with the muon, which is its decay time, right? And that decay time is affected by relativistic effects, because the muon moves at a speed which is comparable to the speed of light. So we have a gamma time dilation factor that comes into it, which means that based on what we discussed in this class, the clock that is associated with the muon, the clock that is attached to the muon as it falls through the atmosphere, runs at a different rate than the clock that we have as a laboratory clock, right? So this is the physics of the process, right? Its lifetime for the pion is very short, but then the muon has a somewhat longer lifetime, which is very well known, and the muon arises decay of the pion. It turns eventually the muon decays into a positron if it's a positive muon, or if it's a negative muon, it decays into an electron, plus neutrinos, which are not seen. So this is kind of a very nice setup to test whether special relativity is correct. These kind of experiments were done already in the late 40s and 50s. And so it's a Feynman diagram description of the process. And so the first thing you do is a non-relativistic calculation where you estimate, the distance that the muon will travel based on its lifetime, right? And you expect that if you have a million muon up at the uppermost layers of the atmosphere, there's going to be about 0.3 that will reach the surface of the Earth because of the muon lifetime being this value and the distance being about, say, 10 kilometers, right? This is kind of calculation that you want to do. You want to pick some sensible number that is easy to work with and a speed which is very close to the speed of light so that you have a gamma factor which is significant. Remember, these initial cosmic ray protons are very energetic. So the muons, as a result of this cascade process, are also moving quite fast. And so now when you do the relativistic calculation, you take into account the time dilation factor. And the time dilation factor is very significant because you get a gamma, which is about 5, which means that you have a lot more muons that reach the surface of the Earth than you would expect if you had not taken into account the time dilation effect, right? And so you have many more. And so you can measure this, and you can see that indeed, because you get so many more muons on the surface of the Earth, you have effectively measured the time dilation effect. And so what is interesting in this particular case is that you can view this process from the lab frame, but because of the ultimate democracy of special relativity, you can view it from another reference frame, which is an equivalent one, of course, just as good, right, which is a rest frame that is attached to the back of the muon. Right, and so if you do that, what happens is that in the muon frame, the end result is of course the same, but instead of having a time dilation, you have, because the muon is moving so fast, you have length contraction. Right, so he thinks that the distance is not 10 kilometers, but is much shorter because of the gamma factor that contracts space. So either way, you get the same result. You get a lot more muons reach the surface of the Earth, and so this is one of the perhaps earliest test, right, of special relativity, where you test at least this time dilation effect using elementary particles as clocks, right? I mean, it is normally not easy to accelerate a clock, right, your clock that sits next to your bed, to a speed which is 0.98, the speed of light, right? But the muons will do that easily. And so now, nowadays, of course, some of us are involved in particle physics experiments and theory as well. And so the kind of relativistic length contraction and time dilation I was talking about for the muon appear again when you have an accelerator experiment, because particles there are also accelerated at speeds which are very close to the speed of light, and so you have the same kind of effect. So if you look at an experiment like the ones that are done at CERN, of course they test special relativity every day because these effects have to be taken into account. So here is the LHC tunnel, and that you might recognize this guy here. So if you look, for example, at lifetime experiments, again for the muons are ideal kind of clocks because they last for quite a while. Their lifetime is not too short. And so again, we're talking about gammas, right? The gamma is listed somewhere up there, and so it's a significant relativistic effect that comes into play. So this is all I'm going to say about special relativity, as I think some of you might have known about this muon decay stuff. So we started discussion of general relativity by pointing out the importance of the equivalence principle, right, and the fact that there is always some special reference frame that you can find in an arbitrary gravitational field, which is associated with a freely falling particle, right, and a freely falling frame. And so the main consequence is that you cannot distinguish between an acceleration and gravity. They're basically the same thing. There's no one way to tell one from the other. And so here's a couple of pictures that illustrate what I'm talking about and what we discussed in class. That is, in the first case, you have a particle that is on the surface, an observer, a person, that is on the surface of the Earth, and he is experiencing a gravitational field, and as a result of that, bodies are attracted to the Earth. And you can mimic this gravitational field by having actually an elevator or a rocket that is accelerated by exactly the same amount. And if the observer has no way of looking outside the rocket, in other words, if there is no window, then there is absolutely no experiment that will tell him whether the first or the second situations are realized. They're basically identical as far as the physics is concerned. And that is, of course, the statement of the principle of equivalence, right? And so as a result of that, if you have this special frame, which corresponds to a freely falling observer, then you can cancel the gravitational field entirely, just like you can cancel the acceleration. So that applies, the kind of discussions we had apply both to material particles, but also to photons, right? Light is affected in the same way. That is, light, if there is a gravitational field, will be deflected down because it carries energy and it carries momentum, and so will be affected by the gravitational field. The beam will bend down, and if you have an accelerated frame, light will be bent the same way because of the principle of equivalence, right? So you will have the same effect happening in both instances. And the fundamental equation that describes that is the equation of free fall, which we wrote in class, right? So this is one of the, if you wish, one of the two fundamental equations of general relativity, because the equation of free fall is the F equal ma for relativistic gravity, right? It's what takes the place of Newton's equation if you have relativistic gravity. So it is a fundamental equation, except that in class so far we have not really gotten to the bottom of it, right? Because we have been able to write down this equation in terms of affine connection, and we have been able to write the affine connection in terms of derivatives of the metric, which is kind of miraculous that you could do that, right? And so with the proper time here appearing, du and d tau are the same thing. And so this equation of free fall then tells us the orbits are given by geodesics and so forth. But the reason why we haven't gotten to the bottom of it yet is because we don't quite know what the g mu nu is, right? This g mu nu is the metric, but we don't quite know how to determine that. And in order to determine the metric, we will need to write down the field equations, right? And we're very far from that at this point. And so was, of course, Einstein in 1912 or 1911 when he recognized that there was an analog of F equal ma, but he wouldn't quite know what would determine the g mu nu, right? So what the g mu nu is exactly, we don't know yet. We only know what the g naught naught is, right? We know one component out of 10. The naught naught component is related to the Newtonian potential, right? So as a result of that, this equation, as beautiful as it is still incomplete because we don't have knowledge of the gravitational potentials. We don't have knowledge of all of these gammas that are the analog of the force term in non-relativistic gravity. So here's a picture of a geodesic, right? So according to what we learned in class, the particle will follow the shortest or longest path in four-dimensional space-time. That statement is equivalent to solving the geodesic equation or the equation of free fall. So, of course, one of the first things that one might be curious about after what we discussed in class is that it seems like one of the cornerstones of general relativity is going to be this principle of equivalence, right? First discussed by Galileo. And so the question is, is this principle really as good as it sounds? So is it something that we want to really base a theory on? And to what extent can it be tested, right? And so the first tests of the equivalence principle, right, that all bodies fall with the same acceleration due to gravity in the absence of friction and drag and so forth, the first really systematic and very accurate tests were done by Eötvös, right, around 1905. It was a Hungarian physicist in Budapest. He constructed what is essentially a torsion balance. I'll have a picture of that in a moment. And he studied whether this equivalence, right, it comes down to the equivalence of inertial and gravitational mass, whether this is really true for all sorts of different materials, right? You had lead, wood, iron, rock, you name it, right? You put all these different materials in, and you see whether, in fact, all these accelerations are always the same and are completely composition independent, right? So there's a question of whether the effects depend on the material, and his answer was no. It looks like this principle of equivalence is pretty solid. This was, by the way, slightly before Einstein started to write down his equations. And of course, nowadays, we have progressed very significantly. Eötvös experiment was extremely accurate for his days, right? So it was really quite an achievement back then. But nevertheless, since then, there have been other similar experiments. They're very much based on Eötvös' original idea of having a torsion balance, but they're just very much improved because of the way you construct this balance in the materials, in the wire that suspends it, which is a quartz fiber as opposed to a steel wire, and the electronics and the data acquisition that comes with it, the cooling and so forth, so that you don't have any sort of undesirable systematic effects. And so we're down to basically the message you get out of this is that the principle of equivalence seems to be good to 1 part in 10 to the 12, maybe 1 part in 10 to the 13, right? And that, in fact, some of the best data, I said most of it is based on torsion balances, but in fact, some of the best data nowadays is coming from lunar laser ranging, where you measure the distance between Earth and Moon to great accuracy over long periods of time. And this can be done because one of the Apollo missions, and I forget which one, maybe 11, left a mirror on the moon. So you can send a laser to that mirror and receive it back and do very accurate interferometric distance measurements. So that's very nice because it looks like this principle of equivalence is pretty good, right? 1 part in 10 to the 12 or 10 to the 13 is something that you should really take seriously. And so here's a little bit of a detail about Mr. Eötvös's experiment, which, as I said, was done at the beginning of the 20th century. And so he had a torsion balance, which means you have 2 masses that are suspended by a wire, right, long wire, thin wire, and there's a mirror in the middle. And so if these masses, right, if the bar of the torsion balance is moving, you can see this movement, and he actually had a telescope, so he watched this mirror from quite a distance, and so you can detect extremely small rotations of this torsion balance. And the reason why this tests the principle of equivalence, remember, the principle of equivalence states that inertial and gravitational mass are the same. The gravitational mass comes in because you have the attraction due to gravity, right? The inertial mass comes in because you have accelerations due to the fact that the Earth is rotating. So you have a centrifugal force, right? And so the two, the effects are calculable, and if the principle of equivalence is correct, then the masses that come in are the same, so they kind of cancel out. So you expect that there should be no effect depending on the composition of the 2 balls and so forth. And so he did these very accurate measurements that I described in the previous transparency. By the way, this is taken from a review which is very recent. It just came out, I think, a couple of weeks ago by Cliff Will on tests of general relativity. He does a long survey. It's about 70 pages long, all sorts of different tests. And of course, at the beginning, he talks about special relativity, and then soon after that, the principle of equivalence. So it's very nicely done. And so kind of related to this issue of how solid are the principles on which Einstein and we base general relativity today is another related question of whether G, Newton's constant, actually is a constant, right? So you can imagine that one of the concerns you might have is that G has a different value on Earth than it has on Jupiter, and maybe on the Virgo cluster it has a still different value, so that there is some spatial dependence on the value of G. And furthermore, it could vary with time, right? So it could be that if we go back to the early stages of the universe, that G had a slightly different value. And so that would mean that G depends on T, and that, by the way, would be something that also would be not easily accommodated by Einstein's fields equations, right? G is strictly a constant in there. And so over the years, there have been increasingly accurate measurements on how G over G dot is non-zero, right? And so we're talking about variations of G dot over G over times which are comparable now to the age of the universe, right? And so it looks like if G is varying, it is varying by a very small amount that is not easily detectable. And well, this variation of G, of course, falls under the general rubric of whether coupling constants in particle physics, in the fundamental interactions, whether they change in time or not, whether, for example, the fine structure constant is constant or not. And so you can see again that also in the case of fine structure constant, if there are variations, then alpha dot over alpha is fairly small. And this is a debate that has been going on over the last 20 years at least, of whether actually alpha is a constant or not. I think at some point there were claims that it wasn't, based on some results that had to do with a uranium mine in the Gabon. And, but if there is a change, then it is a very small one. So now, one of the things that we talked about in class is this time dilation, right? In the last lecture, we saw that if you have a gravitational field, then you have a gravitational redshift, right? That is something that, in fact, is very easy to calculate. We don't need any sort of sophisticated field equations at this stage. Just the fact that we do know that the equation of free fall has to be correct, right? Because it's derived just by changing coordinate systems. And so that's a credible equation. And the other ingredient that was necessary is the relationship between the metric that appears in the affine connection and the Newtonian field phi, which we have here. And that's the key ingredient here, is that the G naught naught is related to phi. And so that means that we can stick this into the equation of free fall. And if we have a slowly varying gravitational field and the particles are not moving significantly, so that all the velocities are kind of negligible, then this equation is easy to solve. We don't need to know the other potentials. We can just get away with knowing phi only. And we end up with a result that looks like this, where the time in one frame is related to the time in another frame, say the intrinsic time of the clock, by a factor that involves the gravitational field, say on Earth, right? Which is something that we can easily establish, right? And so the consequence that we saw in the last lecture was that you can now write down the frequency shifts for different clocks located at different heights, for example, and therefore in different gravitational fields. For weak fields, it's just a difference in the fields, which is very easy to calculate and work with, right? So an effect that leads to a very simple formula in the end. And so that means that if you have a clock which is high up in a gravitational field, it will run a little bit faster than a clock which is down on the surface of the Earth, right? And we saw that we had an expression for the time dilation, which for a point source was something like this, right? And the formula we derived was for weak fields, but in fact it turns out that that formula is very close to the right result, even if the fields are not weak. And so you have this time dilation even when the fields are very strong, like in the presence of a very massive object, which is rather compact, which is what now is described as a black hole, following Wheeler. And so in the case of a black hole, these time dilation effects are very significant. In fact, you can see this argument to the square root can go to 0. Right? So you can have dramatic effects. And so we're going to talk about that later on in this class. But here we'll talk about something that is more simple and which is easily detectable and can be used, in fact, as a test of general relativity, which is a so-called twin paradox, right? The fact that you have an observer that stays on Earth and another one which flies away in a rocket and goes on a very long trip around the solar system or maybe even further out, and then comes back at a later stage and discovers that the clock on the observer that has been away for a long time has been running more slowly compared to the one that is attached to the stationary observer. And so this kind of twin paradox situation can actually be implemented in a very precise experiment, which is this Heffelheim-Keating experiment, which was done originally in 1971. And so I I won't go through all the details of this, but the idea is that these people took some very accurate clocks on just a regular airline flight, right? So they took these cesium clocks, and they're pretty bulky, as you'll see in a moment, and they loaded them on an airliner, flew around the Earth a few times, and in fact, they first flew one way, and then they flew the other way, so going around the Earth in one direction and then the other direction. And after they've gone through these several airline flights and horrible airline food and so forth for 3 days, they happily came back to Washington, D.C., where they had a reference clock. Right. So there was a reference cesium clock in Washington, D.C., and they could compare whether you actually had this time dilation effects, right, where you were, when you were up in space, right? Because an airliner, after all, flies already back then, would fly at something like 30,000 feet, right? So you would see the effects of the fact that the gravitational field was weakening. And so they found that there was indeed a loss or a gain of just a few nanoseconds, right? But it was significant enough that it could be measured with some reasonable error. And that loss or gain of the clocks that were carried on the airplanes over these 3 days that they went around was measurable, right? And was consistent, in fact, with relativity, right? And so here's a picture of the atomic clocks. As you can see, this is one that they used originally, apparently, one like this. They had several of them, right? Finely tuned so that they would all agree in Washington, D.C., on Earth, right? And this is like a modern version of the same thing, and which is somewhat more accurate, but it relies on this key ingredient, which is this cesium atom timer. So here is another summary of what they actually measured and what they calculated on the eastward and westward journey. They first tried to estimate what the theoretical prediction was in both cases, and then they compared it with their measurements. And as you can see, the measurements are actually quite close to the predicted numbers. Now, it's not as simple as it looks, because in this case, both special relativity and general relativity come in, right? Because you have, first of all, the gravitational redshift, which just has to do with the altitude at which the clock is located, right? Has not much to do with the movement. But there is also a special relativity effect, right, which is comparable in this case, because the airliner is moving, right? Is moving. In fact, the Earth is rotating as well. So you have to understand that your reference clock, if you want to use a reference clock, it should not even be located in Washington, D.C. It should be located at the center of the Earth, right? Because the center of the Earth would be a more appropriate inertial reference frame, because that would be kind of sitting still there, more or less. Not quite, because of course the center of the Earth is moving as well, right? So you have to take into account the fact that the airline is going this way or that way, but also the clock that is in Washington, D.C. is moving as well. So those have to be taken into account. And you have to take into account the fact that the speed is not zero, so that there are special relativity effects. So you have, in fact, a gravitational effect, and you have a kinematic or special relativity effect, which in this case, you see there is a significant subtraction. It turns out that those effects are comparable in magnitude when you do this specific experiment, which has to do with a certain height, right? It's an average height, yeah, at which the airplane is moving, and has to do with speed, which is, of course, not always constant. The plane eventually lands, but you can estimate what the speed is on the average and take those effects into account. The gravitational redshift, in fact, is the easiest one to calculate, because that is just affected by the height. And usually a plane, when it flies, you know, from here to Washington, D.C., or wherever it is, well, it takes off, but then it cruises around at about 30,000 feet for most of the flight. So that height is pretty much constant over most of the flight, which could be something like 4 or 5 hours. So the relativistic, general relativistic correction is easy to sort out and is easy to predict. What is somewhat more complicated, and I won't go through this, is the special relativity one, because the special relativity has to do with all these velocities that are involved. and at some point brings into play also the Earth's rotation speed. And so that goes into that number. So basically their experiment was able to detect this twin paradox effect, right? But it was a combination of both special relativity and general relativity correction that came in together with sometimes even with opposite signs, right? And so here is another test of one of the principles of general relativity, and that is whether it is actually possible to have an equivalence of gravitational inertial mass which does not depend on the orientation, does not depend on the distribution of nearby masses, and would cause some sort of anisotropy in the inertia, right? So people have tested whether there is actually an anisotropy in the inertia, which would be affected, for example, by the presence of a very massive nearby object, the center of our galaxy, right? So one of the earliest experiments to test this anisotropy of inertia is due to these people, right? And so it's referred to as a local position invariance. And so you can, actually this is a different thing. This is testing whether the gravitational redshift depends on the potential the way we just discussed. So actually this comes later. So I was thinking about something else that I'm going to talk about later in the lecture. So another interesting application of the gravitational redshift is in global positioning systems, because global positioning systems rely on a constellation of satellites, right, that send a signal and allow us then to position exactly ourselves on the surface of the Earth based on the various time delays and time differences between the signals that are received from different satellites. And those satellites are fairly high up and they're constantly moving around. They're not geosynchronous. And it turns out that general relativity plays a role in this GPS system, because it is, as I say here, it is continuously operating experiment in both special and general relativity. Right? Special relativity having to do with the fact that these satellites move, and so you have to take the relativistic correction into account. Remember, they're very small, but if you have a drift, then that will give you a drift in the position where you're at on the surface of the Earth, so you have to correct that, right? And so at the intersection of these signals, you can then find where you're located, and here is another picture of this GPS constellation and one of the GPS satellites. We're talking about 31 satellites in various planes and at about 20,000 kilometers of altitude. And so they orbit the Earth in about 12 hours, and they carry clocks which are accurate to nanoseconds. And of course, we saw that already from the previous discussion of the airliner experiment, that these clocks have to be quite accurate to be able to correct for the effects of general relativity. And so again, in the GPS system, you have corrections which are, on the one hand, due to special relativities, because these clocks are moving at a velocity v, and these effects of the order of 10 to the minus 10. And you also have the relativistic correction that we discussed in class, which has this form, right? In class, we have the speed of light, which is equal to 1, so we didn't have the c squared. And that correction at this height, right, at the height that we discussed before for the satellites, is about 10 to the minus 10, which makes it comparable to the special relativistic correction. So you have to take that into account, because if you do not take into account the general relativistic correction, then you do find that the GPS would drift by about 300 kilometers in a month, right? And that's a big drift. It's a very big drift. So the GPS system has to take the general relativistic correction into account. Otherwise, the position determination would be completely off, right? So the GPS systems are, in fact, a test of the things that we learned so far in the GR class.
I have a question.
Yes?
The difference that comes when the plane goes from east or it goes to west is due to special relativity, right?
Yes. Yes. So, any other questions or comments? Were you aware of this fact that the GPS system have to take the relativistic corrections into account, that the drift will be quite large? Yes. So now we come back to our regularly scheduled lecture, right? And so one of the main things that we learned in the last lecture was the central role that is played by the equation of free fall. Or geodesic equation, right? So we have that the second derivative of x mu with respect to tau squared plus gamma mu lambda sigma dx lambda dx sigma by d tau is equal to 0, right? And so we also learned that gamma was equal to 1/2 times g to the minus 1 of dg plus dg minus dg, some combination of derivatives of the metric, where the metric is defined by the proper time interval as minus g mu nu times dx nu, right? So the proper time interval that appears in the geodesic equation is this d tau here, right? And so we discussed the fact that you don't really quite know what to do with this equation unless you know, of course, what the metric is, right? The metric depends on x. And so if you know the metric, which is the gravitational field, then you know the affine connection because you just have to calculate those derivatives and you stick it into the equation of free fall and you will get the analog of Newton's equation. So this is the relativistic of F equal ma, right? Or x double dot if you want, right? Where F is minus the gradient of some gravitational potential, right? So this is the relativistic analog of that equation, and it is completely equivalent to it. There are a number of important properties that we should notice at this point, in particular the absence of the mass, right? The mass has disappeared, right? There is a mass here in Newton's equation. This would be the inertial mass. There would be a gravitational mass in the potential as well. And because the two are the same, of course, the mass eventually drops out. And in the equation of free fall, such a mass is never present, right? Which accounts for the fact that the motion is geometric because all bodies will follow the same type of trajectory, which can be interpreted as being due to the geometry. So in other words, all bodies follow the equation. Integral of d tau, variation of that is equal to 0. Right? These two equations are equivalent to each other, right? We spent some time proving that, and it is a very important ingredient and very important notion to understand that the equation of free fall is equivalent to the equation for geodesics. And so so another way of viewing this equation is that it is the same as the Lorentz equation for electromagnetism, right? In electromagnetism, the trajectory of a particle is determined by the Lorentz equation, which involves the E and the B fields, right? And so this is the analog of that. The Lorentz equation is in fact fully relativistic, right? And we can write it in the relativistic form, and we did that in the second lecture, I believe. So here you have the analog of the Lorentz equation. So you have the equation that tells you what trajectory a particle will follow when it goes from point A to point B under the influence of gravitational forces, right? Analog of the Lorentz equation for gravitation. So as I said, this is one of the cornerstones of general relativity. It is one of the cornerstones of the relativistic theory of gravity, because this equation will stand, will not be modified. We are going to have this as one of the fundamental equations. As I mentioned before, of course, the key ingredient that is still missing is what determines the g mu nu, right? What determines the G mu nu? Because if we pursue the analogy with electromagnetism, then electromagnetism, the field is determined by Maxwell's equations. Right? We solve Maxwell's equation, you get the E and the B fields, and you stick that into the Lorentz force equation, and you get the trajectory. Here the problem is that we don't know what the G mu nu is. Well, we know that it is a metric, but that is not sufficient to determine what the actual values are. The only thing that we were able to establish is that G naught naught, right, was equal to minus 1 plus 2 phi, where phi is, if we have a point charge, then this is minus gm over r, right? So if we have a point charge or point source, right, then this is the phi that we need to stick in there, right? And so if we have a point source, then minus g naught naught, or g naught naught, is equal to 1 minus, right, 1 minus 2 mg divided by r, plus possibly dot, 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 because this was obtained in the weak field limit. Right? We assume that the fields were weak, which means that the G mu nu was approximately equal to an eta mu nu, right, plus higher order terms, so that the metric was considered to be close to flat, right? So, well, this of course is one key ingredient as well, right? And the problem is that it only gives us one of the fields, right? And there are 10 of them. G mu nu has 10 fields because it is symmetric tensor in 4 dimensions, so there's 10 fields. We have one, and we need to determine another 9. Now, what are the remaining 9? Well, again, the analogy with electromagnetism will tell us that we have basically determined kind of the analog of the Coulomb field, right, the phi. And, well, that's just a small part of the electromagnetic fields. We need to have the full E and B fields, and that's in particular that will involve vector potential, right? So here we're missing the greater part of the gravitomagnetic and gravitoelectric fields, right, which are the additional components of the metric, right? We can think of the metric as being composed of the G naught naught, and then the G naught I and GI naught, and then GIJ, right? So we're completely missing these ingredients, and that will be some work. That will be some work, because those will be determined by the field equations, which are the analog of Maxwell's equations, right? And we're a long way from that, and Einstein, of course, was a long way from it as well in 1911 or 1912, where we started to realize that this was the correct equation, but you needed to know the G mu nu, right, in order to be able to make some sensible predictions. Right, so nevertheless, we might want to think a little bit about what this means at this stage. And so I'm going to erase some of this stuff and just stare at the relationship that we have just obtained, which is that so that we obtained that d tau squared is equal to minus G naught naught and times dt squared. And so this is equal to 1 minus 2 mg, or small mass, times g divided by r times dt squared, right? Plus, you know, in the weak field limit, which is this result up there, right? And so this was obtained by looking at the correspondence between the relativistic equation, the equation of free fall, and Newton's equation in the limit where space-time was almost flat. So this was obtained from an almost flat metric, right? Which meant that G mu nu was written as eta mu nu plus a small part. In fact, the small part was written as h mu nu, right? So that meant that we were considering a situation where we have a mass, which is a source for the gravitational field, and that the effect of this mass at some point goes to 0 because the gravitational field decreases in strength as you go away from the source, which is one of the reasons why you can actually use this. And so such that h mu nu, right, goes to 0 at infinity, right? H mu nu goes to 0 at infinity was one of the things that we used. And because the field goes to 0 at infinity, that's why you get this 1, right? So when you go for sufficiently large distances away from the source, then this term goes to 0, and you, in fact, recover the flat metric, right? So when r goes to infinity, you get 1 times dt squared, which is this not component of 8 alpha beta, which you remember is equal to -1 and then 1, 1, 1, right? So it is this -1 here. This -1 here, right? And, well, the problem is that if we look at the universe surrounding us, it doesn't look like all the masses disappear past a certain distance. In fact, the further you look out, the more bodies you see, right? And so the question is whether this argument is actually complete, or whether one should try to think about it a little bit more. And so the point is that if we consider quantum mechanics, right, then in quantum mechanics, the time evolution is given by something that looks like e to the minus I over h bar, right, times the energy times the time, right? That's the time evolution operator that we learned in the quantum mechanics class from last quarter and the previous one, right? And so what appears in the exponent is the energy. Well, if you have a particle at rest, then the only energy you can really have is mc squared, right? So let's take that. Let's take a particle at rest, and let's just put the rest mass, and then we have the time, right? And now, quantum mechanical propagation has to do with the time scales, right? Because if the time scales are the same everywhere, right? If the time scales are the same everywhere, then we can draw a diagram where we have t and we have x, so just one dimension to make it simple. Then if these time scales are the same, then the phase is the same everywhere, and particles propagate with some sort of plane wave, which looks like this, right? The propagation takes place in this way, right? Now, if the time scales are different at different location, right? So if the time scale is different at this x from what it is at that x, then of course the particle will move in the direction where the gradient of the phase is the largest, right? So if the time scales are different, then we have that the particle will no longer move in a straight line, right? So this is again x, and this is t, and so we have something that looks like this, and the particle will now move, as I said, in the direction in which the gradient of the phase is the largest. So these time scales seem to affect the propagation of the particle, and in fact that is the reason why this factor has in fact an effect in the way the particle moves at the classical or at the quantum mechanical level, because this is in fact causing some sort of attraction that makes this curve, right? And so it is natural, therefore, right, this argument is, I've introduced it because it is something that justifies to actually look at this seriously, right? So this one, the origin of that one, we're going to focus on this one here. The origin of the one is coming from the fact that we expect the fields to go to 0 at infinity. And as I said, that is not quite the case, because we could expect that, in fact, we should have some other contributions, right? And in fact, this term is due to inertia. Is due to the inertia, and so we'll come to that in a second. And so let's say that instead what we want to do is we want to sum up of all sorts of different particles. So instead, write that d tau squared, right, should not just contain the contribution from one particle, but should contain the contribution from all sorts of other particles, which have to do with Jupiter and Saturn and nearby stars, and then the center of our galaxy and so forth. So we will write it as m1 over r1 plus m2 over r2 plus dot 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 mn over rn, right? And then times dt squared, right? So each one of these terms is kind of a remnant of what we had before, and we're going to be cavalier about the signs. We'll come back to that in a moment. And so this is a sum of all possible bodies in the universe, right? Well, in order to make some progress, we are going to state that all the ones that are far away, we're going to lump them together into a single term. And so we're going to write this as the total mass of the universe, right? So all the faraway galaxies, nebulae, and so forth, we're going to lump it into one term, and it will fall off like 1 over the distance, right? That's an assumption that we make here, but seems like a reasonable one. And then plus the body in question, which is us, for example. So plus m over r, right? And then times dt squared. And so that is somewhat different, right, from what we have up there, because the 1 has been replaced by this term. And now what we can do is we can write this as mu over ru, right, times 1 plus, and then ru over mu times m over r, and then times dt squared. And so now we've been able to bring in the 1, right, bring in the 1. And now what we will do is, of course, something that is very sensible to do, and that is to rescale the time, right? So we are going to define dt prime to be the square root of mu over ru times dt, right? And so that is kind of a redefinition of what we mean by the speed of light, right? And so we end up with d tau squared d tau squared is equal to 1 plus, so let me write it as 1 plus ru over mu times m over r, right, times dt squared. So in other words, I've called dt prime, I called it back dt, and so I'll have that. And so this is what I should compare this expression to the one we had before, right? And in fact, they look rather similar, because there is certainly a 1 over r, and I would conclude that, in fact, the g that appears over on this side, right, there is a g here, that is related to the total mass of the universe, and the total mass, the radius of the universe, and the total mass of the universe in this relationship, right? Which can be written also as 2 mu times g is equal to ru, which is in fact what we shall see later to be the Schwarzschild radius. And now all these concepts are kind of not really defined in the most precise way, right? Because we're talking about the radius of the universe, right? And so the question comes up, what is exactly the radius of the universe? And well, we can estimate what it is more or less, and how can we estimate it? Well, we do know that there is an age of the universe, which is about 13.8 billion years, right? And so using the speed of light, you can translate that into a distance, which is going to be our working number for the size of the universe within a factor of 2 or a factor of 4, something like that, right? And we're talking about the visible universe, right? Sizable visible universe. And so if you use, right, so age is about 13.8 gigayears. And I'll suggest that you do this as an exercise and verify that this is indeed in the right ballpark. This will give you about 10 to the 28 centimeters. Right? We're kind of using particle physics units. An astronomer will probably not use centimeters, but we will. And the mass of the universe, well, that is not known precisely, but we are not talking about precision here. We're talking about order of magnitude estimates. And one knows that given, a few orders of magnitude plus or minus, the mass of the universe is about 10 to the 80 times the mass of the proton. There's about 10 to the 80 protons in the universe. And so that allows you to then estimate this ratio, right? You can use, it is convenient to use a system of units where h bar c is equal to 1, and that is equal to 1 Fermi times 200 MeV. Right, so you can convert a mass. This is about 1 GeV. So you can convert this into a distance, and in fact, this is correct. You find that in fact, indeed, 2 mu times g is approximately the same as Ru. So there is this, in fact, this numerical coincidence that is between Newton's constant and the size of the visible universe and the mass of the visible universe. And so the argument that you get from here is in fact consistent with this other numerical coincidence. Now, which by the way leads to another interesting result, which I will mention here as well because we're talking about this stuff. And that the total mass, if you take the total mass of the universe and you add to it the potential energy, that is m squared times g divided by r, and that is approximately 0. The total energy of the universe is roughly 0. That is, the total mass seems to cancel out the potential energy as well. That is just a consequence of this relationship. So now there are a number of problems with this, right? There are a number of problems with this argument, right? With this argument, right, saying that this is actually equal to 2g, right? And the problem is that the sign is wrong. Sign is wrong. That is, we should get a minus sign and not a plus, right? Well, what I just presented you is the argument that Feynman makes in his lectures on page 72. So how does Feynman get out of this bind? So how does Feynman say that, well, we can change a minus sign into a plus sign? Well, his argument is that this is in fact a very naive calculation because we're not including in the proper time interval, right, in the tau squared, we're not including all the other components, right? This is equal, of course, to minus g mu nu times dx mu dx nu, right? And so this is equal to minus g naught naught dt squared. But then there is the other component. So there is the minus g naught I dx naught, which is dt again, times dxi plus the gij terms, right? So we have ignored all these other results, right? And so as a result of this, it is not clearly a credible calculation at this point, but he interprets it as a hint of what this 1 signifies, right? Because he claims that the 1 is due to inertia. Is the inertia contribution? He says the reason why you have this 1 is that it arises because there's actually other contributions, and those other contributions can be scaled out. They can be scaled out so they can obtain a 1 by just rescaling the units of time. And if you do that, then what you seem to gather is a relationship between Newton's constant and some of this huge amount of mass that is distributed in the universe. And of course, what we just discussed here is basically an implementation of Mach's principle. This is basically Mach's principle being brought in through the back door, right? So Mach's principle, of course, states that the origin of inertia is in the distribution of faraway galaxies. And if you didn't have those faraway galaxies, there would be no inertia, right? And that a body wouldn't be quite clear what to define as the mass of an object, right? This m that you use in Newton's equation, which describes if its inertia, if there is no mass distribution at infinity, because that would not cause a frame of reference to what the behavior of this body is, whether it's accelerated or stationary or moving at a uniform velocity or whatever it's doing. In the absence of the faraway bodies, there would be no frame of reference. So this is a way of introducing Mach's principle. And so it's a good point in our lectures to bring this in, because it turns out, and in fact, Feynman is obsessed by this whole idea of what exactly the metric is and why there is a 1 in the metric, and what if include these concepts about inertia in the construction of general relativity, does it make a difference, or is it something that is already part of general relativity, or what? So now, we're going to leave this topic, right? We have just a little bit of time left. And we are going to discuss in the next lecture the principle of general covariance, which allows us to write down eventually the field equations. And one of the issues that has come up, and I think I discussed it very briefly in the case of the presentation that I had a moment ago, is whether in fact the principle of equivalence holds, right, exactly to great accuracy, maybe 1 part in 10 to the 12 or something like that, and because it is one of the pillars of general relativity. And let me mention, because Weinberg mentions it and a number of other books also mentions it as an important result, one of the tests that was done, right, was to see whether inertia, right, this resistance of bodies to acceleration, actually has some sort of directional dependence, right? Whether inertia is sensitive to nearby masses. And so this was the experiment that was done, already in the 60s by Hughes and Drever. And what they did is, so tests, anisotropy of inertia, right? Because if these ideas are correct, right, if what Mach has been saying and what Jordan and Brand-Sticky and Feynman have been talking about, then the origin of inertia is in the distribution of faraway bodies, faraway galaxies. Well, they don't have to be that far away, because one of them is nearby, right? In particular, the center of our galaxy is very massive. So that should exert an influence, and that presumably can be tested, right? So this Hughes and Drever experiment, what they did is, they're of course on Earth, right? And the Earth is rotating, right? So they do an experiment in which they do look at energy levels in an atom, and what they used was in fact lithium-7, right? It really doesn't matter that much of what type of, it's been repeated with a number of different atoms in different setups, right? And so what you look is at the splitting of levels in a magnetic field, right? You remember that if you have a B field, then you have a Zeeman effect, right? And that the levels, if you're dealing with a level that is characterized by total angular momentum J, right? The JZ component will be between minus J all the way to plus J, right? And so you will have 2j plus 1 levels. And if there is no magnetic field present, then you would expect that there would be a degeneracy, right? The degeneracy of these levels will reflect the fact that there's isotropy, right? And there is no special direction. We talk about that often in the quantum mechanics class, that rotational invariance will give exact degeneracy between the z components of the angular momentum. And so what they did was an experiment in which they have this lithium thing, and it is, right, so the experiment is done here, and because of the Earth's rotation, there is maybe a B field along this direction, and because of the Earth's rotation, at some point, the B field is going to, and the whole experimental apparatus is going to face in a different direction, and what we have here is presumably a very massive body, which is the center of our galaxy. Right? So the whole experiment is going to be moving and rotating with respect to the location of the center of the galaxy, which is a first approximation is completely stationary, right? Because this period of rotation is fairly short. And well, what they found was nothing, right? So what they found was that the effect was less than 1 part in 10 to the 20. One part in 10 to the 20, and in fact this was in the early 60s, and lately these kind of experiments have been repeated, and again they're discussed in the Cliff Will review of a few weeks ago. And the present accuracy is, well, depending on who you believe and whether you accept the systematics of the experiment, anisotropy of inertia has not been detected at a level of 1 part in 10 to the minus 27, maybe 10 to the 29, 10 to the minus 29, maybe even a little bit beyond that. So no detectable anisotropy of inertia at this point. And so, which is, in a sense, is good, because that is one of the founding principles, right, of the general theory of relativity, is that you have equivalence of inertial and gravitational mass, and once you put yourself in a freely falling frame, then the effects of all nearby masses are gone, and there should be no preferential direction that would give some violations of special relativity, for example. And so that is very good. So, nevertheless, you would expect that on very large scales, because the distribution of mass in the universe is fairly non-uniform, that at some point there would be some detectable effects. So that still remains kind of an open question, and whether, in fact, Dickey argued that even if there is a slight anisotropy in the distribution of mass, you will still not get any sort of detectable effects in these kind of experiments. So anyhow, this is one of the things I wanted to discuss today. And now we're going to do a little bit, before we plunge into the principle of general covariance, what I want to do here is a little bit of mathematics, right? Because it is clear that we are going to deal with curved coordinate systems, right? Coordinate systems which are not Cartesian, and where you don't have just x, y, and z, but you have some more complicated coordinate system described by a metric which is not diagonal, right? And so at some point, I think it might be useful to do just some simple exercises, and we have about 10 minutes left. So let me try to do one of the simplest examples that deal with non-Cartesian coordinate system. And so that would just spherical coordinates. So let me talk about non-Cartesian coordinate systems. And I think we are going to learn a little bit about the physics as well by just looking at these simple examples. And so the simplest one is, of course, a spherical coordinate system, because we're all familiar with it and we basically know all the answers, right? So we have x is equal to r times the sine theta times the cosine of phi, with the usual definition of the angles. And y is equal to r sine theta sine phi, and z is equal to r times the cosine of theta. And that defines our change of variables from the Cartesian to the polar coordinates. And so we can invert this relationship, and we can write, of course, r as the square root of x squared plus y squared plus z squared, right? And we can write theta as the r cosine of z over r, right? And phi as the arctangent of y over x. Y over x, right? Which can be useful when we want to calculate derivatives. Now, the kind of exercise we're going to do here is, in fact, calculate the metric, calculate the volume element, and calculate the affine connection, right? So the first thing we know is that we can calculate this d tau squared. Well, now we don't have the time here, right? It's just a three-dimensional space coordinate, so usually we don't use the term d tau for this distance. We're going to use something else. We're going to call it ds squared, right? So it's the distance in this coordinate system. And of course, in the Cartesian system, it is very simple because it is dx squared plus dy squared plus dz squared, right? In the original coordinate system. And now we want to re-express this in the curved coordinate system that is coming from the fact that we have spherical coordinates. And so we calculate the Jacobian matrix of the x, y, and z coordinate system with respect to the r, theta, and phi coordinate system. And so that is just a shorthand for this big matrix, which is dx by dr, and dx by d theta, and dx by d phi, and then dy by dr, dy by d theta, and dy by d phi, and dz by dr, dz by d theta, and dz by d phi. And as you can imagine, these things can be a lot of fun to calculate all these derivatives. Nevertheless, our expressions are very simple, and so it's just a matter of doing a little bit of algebra to figure out what these things are. And so I encourage you to do this in a little bit more detail than what I will be able to do in the remaining 6 minutes, because I think it is really important that we understand how to manipulate these coordinate systems and how to change from one to the other and do the calculations correctly. And so in this case, calculating those derivatives, right, we have the explicit form of x as a function of the other, r theta and phi, or the inverse of that. And so this is equal to sine theta cos phi, and r times r cos theta cos phi, and minus r sine theta sine phi, and sine theta sine phi, and r cos theta sine phi, and r sine theta cos phi, and cos theta minus r sine theta, and 0. And so from this we can calculate. So we have the metric, right, in a sense. We have a change from one coordinate system to another, which will give us the metric. So we have that ds squared is equal to eta alpha beta times d psi alpha d psi beta, as we discussed in the first GR class. But in our case, in Cartesian coordinates, this is just 1, 1, 1, and then 0. In Cartesian system, right? So in a Cartesian system, this is, of course, dx squared plus dy squared plus dz squared, right? But now we want to rewrite this in the other coordinate system, which is the r theta and phi. So this can be written as eta alpha beta times d psi alpha d psi beta, and then dx mu times dx mu dx nu, right? And so we want to write now these derivatives actually as partials. So let's do that. in this way. And, well, what are these derivatives? Well, they're just the ones we calculated. We have them right there, right? So these derivatives are just the ones we calculated. And this object here is our G mu nu. Okay, so the G mu nu is obtained just by taking those entries in that big matrix and evaluating this product. Now you have to understand, though, that you're doing a sum over indices alpha and beta here, right? So we need to do a sum. So, for example, GRR, right? The RR component, right? Remember that these are just dr, 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 d theta, etc., right? The x is our coordinate, spherical coordinate entries. So the first term is, say, when alpha and beta are equal to 1. This, by the way, is a diagonal matrix, so only diagonal entries are meaningful. So the first entry has alpha equal beta equal to r. So that's this derivative up here. Okay. So is dx by dr times, again, dx by dr. Right? And then the next entry is dy by dr times, again, dy by dr, right? Plus dz by dr times dz by dr, right? And only the diagonal entries matter because the matrix eta is diagonal, right? So now we look this up. Dx by dr is this entry here, so it's that thing there, right? So we need to square it. So it's equal to sine squared theta cos square phi plus sine squared theta sine square phi, right, plus cos squared theta. And so that all adds up to 1. Okay? All right, so we've done all this work to determine that, in fact, GRR is equal to 1. Right? So we determine one entry in this matrix. And so the 1, 1 entry in the G mu nu, now, because of the way things are working here, it turns out the G mu nu is also diagonal. So we can repeat the same exercise. And again, we're running out of time. So you can redo this calculation for the G theta theta, right? And so that's going to be dx by d theta twice. So dx by d theta is this entry right here. So it's this guy here, and that's going to get squared, right? And then I'll add all the other ones, and this turns out to be just r squared. And g phi phi is equal to r squared times sine squared theta. So we have learned that in this new spherical coordinate system, the entries, the metric is diagonal, but the entries are not 1. Entries are not 1. Right? So they have things like r squared, and in fact the last one even has the angle appearing in there, right? And so it is diagonal, but not 1, 1, 1, and then 0 everywhere else, right? So give me a couple more minutes, and we can then calculate, right? We can calculate. So we have that G mu nu is equal to, so it is equal to 1 r squared and r squared sine squared theta, and everything else is 0, right? And so it's given explicitly by this. And we can calculate the determinant of G, the determinant of that metric. And because it's diagonal, it's just the product of the elements along the diagonal. So this is equal to r to the 4th times sine squared theta, which means that the square root of the determinant of G is equal to r squared times times the sine of theta. And that the invariant ds squared, right, which was equal to dx squared plus dy squared plus dz squared in the Cartesian case, now is slightly different because it has the form. So this is equal to g mu nu, dx mu, dx nu. So this has this coefficients. So it is equal to dr squared with a coefficient of 1 plus r squared d theta squared. And we can write the second term as r squared times sine squared theta. So times d theta squared plus sine squared theta d phi squared. We can write in this form. Right. So the distance, which is the square root of this thing, contains you know, a number of terms which actually have coefficients which are not equal to 1, as in the flat case, right? And the other thing is that the volume element, so dv, which is dx times dy plus times dz, in the Cartesian case, in this case, it is the square root of the determinant of the metric times dr, d theta, and d phi. And so as a result of that, it is our usual volume element in spherical coordinates, which you remember is r squared dr times sine theta d theta times d phi. So the volume element sine theta. The volume element in spherical coordinates is not just dr times d theta times d phi. Okay, there is this extra factors which are coming from the determinant of the metric. So if you know the metric, then you can calculate the determinant. The determinant will give you the volume element. Right? It will give you the volume. And now, what else can we do in this case in the remaining minute or so? What we can calculate is also the inverse, right? Because we need the inverse of the metric to be able to calculate the affine connection in general, right? In four-dimensional space-times, we need that inverse. And, well, that is very easy to do here because the metric is actually diagonal, right? So if you have a metric that is diagonal, then the inverse metric is just the inverse of the matrix elements. The entries are the inverse of the matrix element we have there. So GRR, remember we denote the inverse by having the indices upstairs. So inverse of GRR is just equal to 1. And G theta theta is the inverse of this matrix element, right? So it's 1 over r squared. And G phi phi is equal to 1 over r squared sine squared theta. Right? It's supposed to be r squared. Right? And so that means that G mu nu is, of course, equal to something along the diagonal, and then everything else is 0. Right? So it is inverse exists, of course. We don't have any issues. And so perhaps the last thing you might be curious about is the affine connection. Right? And that is one stage where you start to appreciate, you know, the value of having algebraic manipulation programs to do these derivatives, because obviously the affine connection contains, right? Remember, the affine connection has 3 indices. Right, it has 3 indices, and it involves the 1/2 times the inverse of G times 3 terms which involve the derivative of the metric. And so this is going to be a little bit of work trying to calculate all these derivatives. And the answer is that gamma theta r theta is equal to gamma phi r phi is equal to minus gamma r theta theta is equal to minus gamma r phi phi, and that is equal to 1 over r. That's what you find. And that gamma phi theta phi is equal to minus gamma theta phi phi is equal to the cotangent of theta divided by r. So what do we discover by this exercise? We discover that the affine connection can be calculated by the formulas that I gave you. It's a little bit of algebra calculating these derivatives. And we also discover that if you have a spherical coordinate system the affine connection, you might have expected that this was going to be 0. 0, because we said, well, the affine connection has to do with gravitational forces. And if you don't have gravitational forces, if you are in flat space, then the affine connection should be 0. Now, are we here in flat space or not? Well, we definitely are, because we started out with Cartesian flat space. Nobody said anything about curvature here. We were in flat space, and we just rewrote the metric for flat space in terms of a new coordinate system, which involves the angles. That has not changed the fact that we are in flat space, which in relativity would be Minkowski space, right? So what we have discovered is that, in fact, even if you choose a weird coordinate system, the gamma is not 0, right? And so that means that the gamma can have some artificial effects. You know, you might think that there is a gravitational field, but there isn't. And the ultimate root for that is in the fact that the gamma is not, in fact, a tensor. It turns out that it is not a tensor under general coordinate transformations. So it can be 0 in one frame, but it's not 0 in another frame, even though there is no gravitational field. And that is what we have discovered, okay? So I encourage you to do these kind of calculations and maybe to verify this result, that in fact the affine connection for this very simple coordinate system, if you go to spherical coordinates, that's what you get, and it's non-zero. So anyhow, that's enough, I think, for today.